Here's a titration curve for us to analyze. Question 1 asks what kind of titration this is. Strong acid, weak acid, strong base, weak base. There's kind of 2 ways I could answer it. Option 1 is to look at the graph. So we've got sodium hydroxide added to an acid. The pH is starting pretty low, maybe about a pH of 1. And then as I add the sodium hydroxide, the pH steadily increases. In the middle, you'll get this big jump in pH. And if you find the midpoint, that is your equivalence point. The point where my moles of acid and base, my moles of hydrogen and hydroxide would equal the stoichiometric ratio from the balanced equation. If you follow that across, you'll get the pH at the equivalence point. When I see the pH is 7, then I know that this must have been a strong acid and a strong base. Now, the other way I could have answered this is by looking at the information given above. 50 milliliters of hydrochloric acid. Well, even if I don't know the molarity, I know that HCl fully ionizes and it is a strong acid. That hydrochloric acid is titrated with 0.1 molar sodium hydroxide, and I know that that is a strong base. Now, it is possible for a weak acid and weak base to also have a pH of 7 at the equivalence point, but that would only happen if the Ka and the Kb were exactly the same. If the Ka of the weak acid were higher than the Kb for the weak base, then the pH would still be a little bit acidic. And that gets into some calculations that eventually become a little bit hairy. And we don't have to do those for the AP exam. So I am safe saying that this is strong acid and strong base. The pH at the equivalence point is then 7. A good indicator for this titration would be, well, I would be given a table of acid-base indicators. If I go way back, we had one given above. And so if I know the pH is 7 at the equivalence point, I want an indicator that's going to turn colors around a pH of 7. And so here my best option might be the bromophenol blue. It would start yellow in the acid. It'll turn green right around a pH of 7. And then it's blue when I've gone beyond the equivalence point and added too much base. Now, the other option is that they might give us Ka values. And it does just happen to be that bromophenol blue has a Ka of about 1.0 times 10 to the negative 7th, approximately. And so if you take the pKa, that's opposite log of the Ka, or here it would just be like the exponent, the opposite exponent of 10. And so if you go pKa, opposite log of the Ka for your indicator, that will also tell you the pH where it'll change colors. So maybe I'd say like bromophenol blue for this particular titration. Bromophenol blue. Sometimes it's abbreviated as BTB. Number 4, how many milliliters of sodium hydroxide were added at the equivalence point? Well, now all I have to do is find my equivalence point and follow it down. So this will be a little bit of an estimate. I don't know, do you want to say like 24 maybe? Somewhere in there, approximately 24 milliliters. And now this becomes the same type of calculation that we would have done earlier in the year when we were just looking at titrations from a stoichiometry lens. What is the concentration of the unknown acid? Well, if I were to write this balanced equation, I've got the HCl plus the sodium hydroxide. It's like a double replacement. All of the ions are +1, -1. So if I replace maybe the positive ions, I'd be left with sodium chloride and HOH, which is also known as water, right? And this should be the typical products of any neutralization. Any acid-base reaction will produce water and some kind of an ionic salt. Now, the reason why I might want the balanced equation is because I need to know the ratio. I need to know the mole ratio between the acid and the base. And now here I've confirmed, I'm pretty confident, that it's 1 to 1. So if I know that the base was 0.1 molar, and I know that molarity equals moles per liter, and so now without stopping the titration, I can use the graph to figure out the volume delivered at the equivalence point. Otherwise, I mean, the way we titrated earlier in the year is totally acceptable, but it's just really hard to stop at the perfect equivalence point. And so these titration curves usually give us a little bit more accurate data. All right, so let's say we're gonna here estimate that it was 24 milliliters or 0.024 liters. Now, of course, we wouldn't have to estimate. If I really had this graph on my computer, I could find that point of inflection, and then I would know the exact volume. All right, so if we cross multiply, this would give me 0.0024 moles of the base, the sodium hydroxide. Now here's where it just becomes stoichiometry, in that I want to use the ratio from the balanced equation to convert from moles of one to moles of the other. Now it doesn't have to be a 1-to-1 ratio. Now it could be, obviously this one is, but if I had something that was like barium hydroxide, BaOH2, or maybe I have an acid like H2SO4. It doesn't have to be a 1-to-1 ratio. So that's why I do need to just consult the balanced equation, because now I know that if it is a 1-to-1 ratio, then moles of base will equal moles of acid. So then I can say, oh gosh, let's squeeze it in over here. Molarity of the HCl would be the same moles, 0.0024, because it's a 1-to-1 ratio. And they have to tell you the amount of acid that you started with. So it looks like we were given 50 milliliters, which blah, 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 would be like 0.05 liters. And now we got it. We'll plug it in, and maybe we'd say that the molarity of the HCl is approximately 0.048, let's see. There we go. Not too bad, huh? Just like earlier in the year. All right, so now the difference was just that we were able to get some of that data off a graph. And finally, in number 6, they want me to sketch the experimental setup. Okay, I suppose. So here would be my burette, and then maybe this is my, whoa, that's a bad flask. There's my flask. The burette would get the solution of known concentration. So here the burette would get my 0.1 molar NaOH, sodium hydroxide. Then down in the bottom, my flask would get the solution that I am titrating, the one that I'm trying to figure out its concentration, or maybe I'm trying to figure out the percent of something in the solution, or we could use this moles. Like once we get this moles, we could use that to find like the molar mass, if I knew the grams of acid used, all kinds of cool things that I could do once I know moles of that unknown solution. So this is going to be my HCl, and the other thing that would go down in the flask is my indicator. And this time we would drip the acid into the base, and the base into the acid, hello, and we would also have some kind of like a pH probe in there. That's why I hooked up to the computer so that we can measure the change in pH over time.